Our guest today is Dr. Imelda Atenzio, is a distinguished scientist and leader at the Air Force Research Laboratory. She currently heads the laser division within the AFRL's Directed Energy Directorate at Kirtland Air Force Base. Dr. Atenzio is responsible for overseeing research in advanced laser technologies, laser effects, atmospheric turbulence, mitigation, and laser system experiments. She's also been recognized for significant contributions to STEM outreach, receiving the Department of the Air Force's 2021 Outstanding STEM Outreach Champion Award. Dr. Atenzio received her Bachelor's of Science in Electrical Engineering from New Mexico State University. She then pursued her master's and doctorate degrees in optical sciences from the University of Arizona in Tucson. Let's welcome Dr. Imelda Atenzio.
Thank you. You did. Thank you. It's an honor to be here back at my undergraduate school. And it looks a lot different. There's new buildings. I don't know if I could find my way around. The streets were familiar, but really appreciate being here. And I just want to thank Professor Steve Stohai for nominating me for this, this honor, and pleasure to be here. So I'm getting over a bug, and I hope I don't have a coughing fit, but hopefully we'll make it through this. So my voice is a little bit off. But anyway, I'm going to talk to you about my career, what New Mexico State, how that fit into it, and the STEM work that I do, and some of the work I do in my current position. So just take notice, if you don't recognize, that's Orion, constellation Orion and the nebula. You'll see why that's important later on. My title, I do this presentation a lot to students at different career fairs and actually all over the place, and I tailor it to whoever the audience is. But really, my love of astronomy led me to the career in optical sciences, and I just wanted to share that all with you. So just, I've kind of already said that. We're going to talk about everything. So I grew up in a little town in northern New Mexico called Dixon. I actually found a cool Google map thing of that, you know, so that was kind of fun. I don't know if I can really find my house, but anyway, but it was dark, very dark. There's like one little street light down the road. And so I was always outside looking at the stars. Loved astronomy with my dad's old binoculars and was always out there. My mom is actually here today, and I owe a lot to her. There you go, Mom. Because I would find out there was some astronomical something or other going on at 2 in the morning, and she'd go out with me and we'd be looking. But I just loved astronomy. And my goal was to become an astronomer as a kid. I didn't really know what that meant. I grew up in the 60s, you know, 60s, 70s. And I always thought my goal about 5th grade, late elementary school, was to sit on the mountaintop with my telescopes, because I just loved telescopes. I'd sit and just look through sky and telescope, or Astronomy magazine, was just fascinated from that. Moved to Albuquerque and lived with my dad and graduated from Albuquerque High School. And so then what did I do? I went to college because my goal was to become an astronomer, or astrophysics, as I discovered that that's what it was called. And I actually went out to California for a year, but didn't really realize how expensive that would all be. Back then, in the 70s, they didn't really have good school counselors to help you kind of guide you on things like that, which is one of the reasons I mentor. And so after a year, I said, well, can't afford that. Came back to New Mexico for in-state tuition, and my sister, who is also here, was here at New Mexico State and in the social work program. I'm still really kind of the only geek in the family. There are more social services, but anyway, and came here to New Mexico State. Still, then I was trying to figure out, do I really continue with physics? At that time, computers were becoming the thing. And here's this EE department, and they had, it was way before they called it ECE. It was an option in the EE department for computer engineering. And I said, oh, well, let me try that out. Took binary math and blah, blah, blah. And I kind of joke now, and some you guys will all get it. And when I tell this to students, some look at me like really odd. But I got bored with ones and zeros. See, nothing against computer engineers. But around that time, or a little bit later, somewhere in that time frame, I don't know, you all remember Dr. Mike Giles, Professor Giles. And he came from he got his degree at University of Arizona Optical Sciences Center. And they were setting up another option under double E, for the lack of a better word of how to call that, in electro-optics. I said, oh, well, that sounds more up my field. And started that, and there was, you took classes out of the physics in the double E department. I'm not sure, imagine it's something similar these days, I don't know. But I know it still exists, because I found a student there I was hoping to hire. But, and so I got my degree in that, and, oh, sorry, I got sidetracked here. In my geometrical optics class, to me, I just loved that. To me, it came naturally. I think I've always really loved light and how it interacts with lenses and mirrors. This is fascinating. Love art and just the lighting of things. You know, I've often thought of volunteering at the plays to learn lighting for plays and stuff like that. But I love light, I guess is the best way to say it, and how it interacts. And I did really well in the geometrical optics class. And I just tell this story a little bit because I'm old now, I just tell all these stories. But the professor says, wait after class. And I said, oh my gosh, what did I do wrong? I was shy then. You know, now I can talk for eternity. Then I was like really shy. And he says, you know, you're really doing well in this area. Have you thought about going into optical design? And I kind of say like, ooh, well, what is that? And so that was my introduction, and to what that really was with optical design. I said, that's really what I like. And what I realized during that period was I myself am a much better engineer. I always have fiddled with things. You know, I took apart my bike. I did all kinds of things, fiddled. Not that I don't like physics, but I really felt that my gifts were more in engineering. And what I really realized also that I loved the instruments that astronomers use, just a tad more than the physics. Not that I didn't like the physics. I still get fascinated with all that. But you could just, I tell people, just put telescope geek across my forehead, and that would be me. I love telescopes. And so I thought, well, I really wanted to go get a master's. How am I going to do that? You know, I felt like I was in debt up to my eyeballs, but nothing like the kids are today, my gosh. But I guess for the time, you know, and I thought, well, how am I going to get to grad school? And I started looking at jobs and stuff, found out they would pay for your grad school. But I found out industry wanted you more to do something specific. And they said, want you to go do computer science. I said, oh, that's interesting, but I had my heart set in optical sciences. And one part they forgot here was that Mike Giles brought over Dr. Jack Gaskell, who was the Dean of Academic Affairs at the Optical Sciences Center in Tucson, Arizona, University of Arizona. And oh my gosh, I was drooling. And I thought, this is the place I have to get there. How in the world am I going to get there for grad school? So I already knew where I wanted to go, couldn't figure out how I was going to get there, and found out, you know, there were places that could send you. Turns out that national labs or government labs were a little bit more lenient on your topic that you could go for. And so my dad had a friend at the Air Force Research Lab, networking, key to everything. You know, you got to network. And I was able to get hired on at the Air Force Research Lab. And let's see, oops, did not mean to hit that. What did I do here? Went on to after I graduated in 1986, I probably forgot a few things here. Let's see, while I was here, I also co-opted the NASA White Sands Test Facility, learned more about how to be an engineer and things like that, and graduated in 1986. But I have to say that New Mexico State really prepared me for graduate school. Probably wasn't as prepared from high school into undergrad, but I was definitely prepared from undergrad to graduate school. So I appreciate all of that and the professors and the introduction to Optical Sciences Center. So I got a job at the Air Force Research Lab, and you had to be there for about 3 years before you could apply to the programs to get you for graduate school. I have to look at the time here because I will go on endlessly. Someone's gonna have to tell me to shut up. But was first exposed to adaptive optics. How many know about adaptive optics here? Probably a few. Okay, we'll talk a little bit more about it. Actually assisted my first job was actually programming one of the Cray computers back then, Cray 2. I can't remember what was there at the time. So, you know, we thought that was really cool. Now after looking at this AI thing that we just did, it's like, dang, it's so old. And I actually worked with David Volz way back in the day in Dr. Janet Fender's branch. Anyway, after the 3 years there, I applied for the program and got accepted. And the program, they weren't as great as they are now. And it was to get it was a training program, and we had to kind of massage it to get it for a degree. And when I was admitted into the program, it was called long-term full-time. They said, oh, you're going to UNM. I said, no, I'm going to University of Arizona. And so we had a discussion on that, and my boss at the time, Janet Fender, was convinced then that that's where I was going, was Arizona, and that was her alma mater. So I started there in a master's degree, and because that was the goal, and then I got PhD-itis. And I realized at that time that in order to teach at a university, you really needed a PhD. And one of my goals was to teach. I had already found that I really like to mentor, coming from a really small rural community where there really isn't that many opportunities and still struggles with that, but it's getting better, is to be able to mentor. And my long-term goal or lifelong goal has always been get, I say, kids of all ages interested in math and science. And so that was the start of my mentoring. Actually was, I think it was Halley's Comet, and I had my little telescope out over here by the stadium, I think it was. And there was a family that came by and was showing them, and they were so excited. And that was kind of like my start. And I started just doing things to help get kids interested. Anyway, because of the program I was on, I was not able to complete my dissertation there, so I had to go back to Kirtland, to Air Force Research Lab, and did it in absentia, which wasn't the funnest of things to be able to do, but I pulled it off eventually. So when I went back to Kirtland, my boss at the time was going to give me time to work on my dissertation, and then things kind of changed. But anyway, I'm not sure if you're aware, but on Kirtland Air Force Base, we have a large telescope facility. I didn't even bring my pointer. The one on the right there, the 3.5 meter telescope. The one next to it's a 1.5 meter. And, oh, this one does not have my twins in it. I should have put up a newer one in there. I don't know if we even have one. But there's now 2 1 meters. And so I spent 19 years of my career there having a blast. Couldn't believe they would pay me to have so much fun. And so I lived my dream. I was on the top of a mountain with my telescopes. It's the Air Force's telescopes, but you know, they let me play with them. And worked in, I wasn't part of when the adaptive optics was really being researched and what's the word I'm looking for? Actually coming to fruition, but I used a lot of this in my career. So here I usually, when I have a piece of paper, you know, it's flat, you're coming in, light from infinity is flat. It hits our atmosphere and it gets basically all messed up, it's turbulent. And you get these intermediate slopes in here, and you get a nice fuzzy blob. And we look at this blob, and we don't know what that blob is, and we turn on our adaptive optics system, and it's actually a binary star. So this technology really was disrupt what they call disruptive technology for the astronomical community. And for those who don't know how it works, so you basically the system is going to measure these intermediate slopes and reconstruct what this looks like. And this video will show light coming in, but trying to get you prepared a little bit because part of it comes a little bit fast. Goes to the primary mirror at the bottom there. Secondary goes back into a system. Systems we have are further, much more complicated than this, but this is a very nice rudimentary example of how this works. And you have light coming in, and that first one is a deformable mirror, thin mirror with actuators that push and pull and change shape, so you hear that blob. And down there at the bottom is a sensor that is actually detecting what this looks like. It's going to give commands back to the deformable mirror. We call it close the loop, and you see it moving. It's actually changing shape to conjugate of that wavefront, or actually such that when it reflects off, it's flat, and in an instant you can correct. And so that was a game changer for many astronomical telescopes around the world, really. And once it was released to the world in 92-ish, I believe, so that's right, David? 92, 93, somewhere in that area. All new telescopes were built with it, and all others were retrofitted. So these are just fun pictures that I have from our laser beam adaptive optics. So what happens is when you're looking at, you need enough light from the astronomical image or object that you're looking at to run that AO system. Many times you're looking at stuff that's really dim. And what the Starfire Optical Range really did perfect was laser beacon adaptive optics. So basically, and this is just for show 3 of them, we just used one, that basically by the mechanism of Rayleigh scattering, the same reason our sky is blue, it's very forward and reverse scattering. So the light, the laser light scatters off the molecular nitrogen and oxygen in the upper atmosphere. And we take that light that's coming back, it's called range gating, so it's at about 16 kilometers up in the atmosphere, and you're taking light from that area, and you're using that backscattered light to run that AO system that and see the dim object that you're wanting to look at. Now, what this work was done on to begin with was at a 1.5 meter telescope. So you can think of it can only go up to about 16 to 20 kilometers in the atmosphere. That's where all the weather particulate is at, and after that it really gets thin, so you don't get enough scatter. But if you can imagine, that's already an error. You really want to emulate something that's like a column. So if you went to a bigger telescope, like 3.5 meters, you're going to get much more error. And that 3.5 is on the right side there. So for years, Dr. Fugate, who is the one that really is the mastermind or who spearheaded this whole project with the help of DARPA, astronomers knew that there was a sodium layer up in the atmosphere about 90 kilometers up and about 10 kilometers thick. And so if you could get a laser beacon to excite those sodium atoms, then you could have a artificial star much higher up and much more equivalent to that column of light. So that one works by resonant fluorescence of the sodium. And so that really was the next game changer. And these are just pictures of, you can't tell what that is on the left, I'm sure, but it's a satellite. CSAT's my favorite satellite only because it's got a lot of structure on it, and you can see that. And so just with using adaptive optics, just with the light from the satellite, you can get all that information, and then you can enhance it with other types of software. And that's part of what my job was at the beginning of my career. Before adaptive optics, I would take data and actually work and program, work on software to take all that turbulence out and come up with an image. But that took days to do. This can be done in seconds. So here's Another one of my favorite ones, just now, Hubble's old, and these are older pictures, but it just shows the example with no adaptive optics on the left, and then with adaptive optics on the right, laser beacon AO. And what's interesting, you see this dark spot in the center, that's not saturation of the camera or anything. It actually turned out to be some cool science on start of a new star, I believe, beginning of a star. I had to go back and look and see that. But Dr. Fugate was able to get Hubble to point to the same part of the trapezium of Orion to compare it to the pictures that we had, showing that ground-based could pretty much do the same as space in the right frequencies with adaptive optics. And so we've used now adaptive optics in many different applications. Main one we were talking about is man-made satellites. Astronomy, astronomers just ate this up. They were so excited about it. Also airborne laser weapons, which is what I work in these days. Laser comm through atmosphere and space. I did a lot of work on that in my prior life out at the Starfire Optical Range. And ophthalmology. I remember there was a ophthalmologist that came over to find out how AO worked, sat with us. And when you go to the eye doctor and they take a picture of your eye back there, it's actually a small AO system in there. And they're actually correcting for the vitreous humor, the jelly-like stuff in your eye. And they're able to see, catch diseases much earlier now. So this technology was transferred to multiple areas. And now I'm in the laser division chief, and in that division, they have worked on high-power chemical lasers. You've probably heard of the Airborne Laser Lab over the years, 20, 30 years ago, in different fruition. But now we're working on electric lasers, much, much smaller, and we've been doing that for probably a good 20 years now, and it really reduces the size, weight, and power. The picture on the right there is like a 1 kilowatt laser. Also look at something called hollow core fibers, and the one on the bottom is it's kind of a hybrid of a chemical laser, smaller, and so actually trying to just reduce the size, semiconductor lasers. And because we're the Air Force, I work for the Air Force, and we want to make lasers that go on planes, we have to worry about aero optics, which is, the aircraft is going really quick through the atmosphere, and that disturbance of the air around the aircraft causes problems in trying to shoot a laser out. And so we do a lot of work with that. The bottom picture there is a small wind tunnel that we have. So in all of this, I have done lots of mentoring. I didn't have a chart on that, but I was talking to Steve or one of you about that, or maybe it was you, David, on that, to let you know that I've been mentoring and parts of different programs almost throughout my entire career, speaking to folks and trying to get kids interested in math and science. And at the research lab, we have a whole STEM program that I've been involved in off and on throughout the years. You had a question? Or did you? No. Oh, okay. Okay. But anyway, I want to thank you very much for this award. It was really a shock. It was like, wow, from my old school. It was awesome. And I realized what an impact New Mexico State had on my career and how well it prepared me. And that's how I found out about the Optical Sciences Center. So that just thrills me. And I'm just grateful to all the professors that guided me. And it's just been an honor to be here and talk to you. And I can answer any questions. Comments, concerns. And I didn't have a coughing fit. Yay.
I'll start off. Thank you so much. Your story is quite impressive, very inspirational. Particularly your site, coming from a small community here in New Mexico, I can certainly relate to that. I'm a small community myself. But I want to ask you about what perhaps some areas of research that faculty may be keeping on their radar in terms of, not only electrical engineering, but also mechanical and aerospace engineering. Are there any areas there that you see perhaps coming down in the future or available now?
I think There's the coughing. Uh-oh. I know that there's a lot of work on hypersonics, and we have some folks doing a lot of that work, and that kind of has a lot of the work ebbs and flows, and it kind of depends. You kind of watch the country and see what they're kind of thinking about and looking at, and we get our signals from the Department of the Air Force, mainly from our headquarters, as we call it, and right now I work in directed energy. So as he said, that I'm that's the directorate that I am in. And directed energy means, for those, it's not kinetic. So it's high power electromagnetics or high power microwaves or lasers are the two things that are considered directed energy. And there's a lot of work going on in both of those areas. And I know your high power area here, I don't know if they've worked with anybody here on the high power electromagnetics, and I'm not as familiar with the stuff that's going on here now. But definitely in laser research, what we're working on more now is, and the effects, like the understanding the effects of lasers on that laser material interaction, understanding how you can damage a threat, for lack of a better word. I'm sorry I talk in government government terms, but I do say that I take being a civilian very seriously. I work. I'm not military. I don't wear a uniform, but just as much do I want to work to protect our country. And so I have that mindset just as the military. And so we're looking at protecting our country and in different ways, or whether it's overseas or here. And so understanding what are lasers and different frequencies, wavelengths, and power levels, how that can affect and defeat a threat, whether it's coming from the ground up, and then that's where you're going through the turbulence, as I was talking with Miranda. And did I get that name right? I get all of a sudden I said, did I remember right? And or you're going air to air or air to ground. And the higher up you go, the turbulence isn't as bad. But if you have a laser on an aircraft, which we keep trying to get done, which is I'm bound and determined to do that, is you have a lot of aero optics effects. So there's a lot of work still has to be done in that, in terms of, you know, the effect of the air just rushing around the aircraft and the turrets where the laser is coming out of. I might have to go with the cough drop here, sorry. I made it through the talk. Because the turbulence is not very thick, but it's very severe as the laser comes out of that turret. And so there's a lot of work being done how to mitigate that and what to do about that. We have made a lot of successes. There's been a lot of different experiments that have happened over the years. But there's look at higher speed AO, types of things like that. But there's also the aero effects, I think the aerospace department, we just hired somebody from there recently. He's actually working on some of this high fidelity modeling of these types of things and computational fluid dynamics, which is looking at what that flow looks like. It's fascinating over the turret and how you get shock waves that really impact the light coming out and reduces that intensity. And so there's that type of work. There's the effects on it, so understanding the type of laser you need and the power levels on just to make that cause damage. And so it's all down at that physics level, understanding that laser material interaction. We also have optics folks that are looking at and controls people. Man, it's hard finding controls people out there. They get gobbled up everywhere. It's just, so put out more controls people. They'll have no problem finding a job. But really the controls of the whole system. You're talking about the laser integrated with the beam control system, which is basically the the optics part to send it out, and a lot of details that go into that. It's I say to make it interact. There's a lot more that goes on in that. I don't know if that answered fully your question, but there's a lot of different areas, and I'm sure I missed some. We have the Star Power optical range. We actually have a quantum optics program going on out there. There's always also work. There's always work with lasers and looking at building new lasers. We're working on 2 micron right now. 1 micron has been kind of the stable, one for a long time. Working on 2 micron, finding out that that has some really cool, interesting properties. And so we're always looking at finding out, is there other things we should be building and should be experimenting with?
Thank you. Can you talk a little bit more about the relationship between the military personnel and the civilian personnel, and if we're giving students advice on whether to enter a research lab from, say, a DOD perspective, or whether it be something, one of the military labs, they went the military route or the civilian route? What kind of advice do you give them for those kinds of
So the civilians are the stability. We're the continuity. The military come and do 3 to 4 year tours with us. They bring different perspective, which is always helpful. We get a lot of lieutenants, so they're newer, and I give them time in the lab because they went to school for a reason. They should be able to learn some of that. The military tends to want to build them into leadership, into officers. And so they don't get as much chance to be able to do a lot of lab work to begin with, but they become leaders, and so they're overseeing that lab work. So if you have someone from ROTC here, rather than from the services like Air Force Academy or Naval Academy or places like that, some of them have been able to do really good research, but they don't have the length of time there to do that. And sometimes it can be a career killer if they come back to the lab. So those are some of the things for the military side. For the civilian side, the military labs are kind of quasi between academic and industry. They're kind of a mixture of that. They're not truly academic, and they're not really truly industry because we don't sell stuff, but it's a really good research environment. And so our civilians have great opportunities to work on cutting edge stuff, that has never been done before. And if you get infused with money from we call it DARPA hard. Are you guys all aware of DARPA defense? Okay, I can't remember what it stands for. We have an expression called DARPA hard, meaning that's what adaptive optics was at the beginning. Could you even measure the atmosphere so you could correct it? And that's what Dr. David Fried was able to, his theory was able to show that, and they were able to prove that. So back to your question. For advice, like when I give civilians, usually they've already chosen to be civilians. I have talked to some students that were trying to decide between military and civilian, and they were going to go to OTS, Officer Training School, and I just what I was saying now. It depends on what you want to do. If you want to be more that leadership and direct technology, you can do it both in civilian and military, but you're definitely going to be doing it in the military. If you want to do more of that research environment, and then as you grow in that, more oversee that, you can do the civilian is more that. So does that answer your question?
Where do clearances fit into that question?
I'm sorry, what?
Where do clearances fit into that question?
Well, to work at the lab, any DOD or DOE lab, and DOE's Department of Energy for Sandia is like Sandia and Lannel, and Air Force Research Lab is DOD. You have to have a secret clearance. So you have to be a U.S. citizen. Way back before 9/11, we actually were able to help sponsor, but we can't do that anymore, non-citizens. So you have to be a U.S. citizen and secret at a minimum. And then depending what area you work in, it goes up higher. So you have to fill out your life story and paperwork. And the government knows everything about me. It's like, any other questions?
How is AI impacting your research now?
Well, we have some folks working on AI in increasing, one thing I didn't talk about was tracking. So when you're looking for a target, you first have to find it and fix on it and then keep tracking it. Even for a telescope, you have to find it up there, find, fix, track, and keep on that. And they're actually been working on AI to see they can do that faster. Also, the big deal now that maybe you haven't heard of, and to answer your question, is clutter. So trying to find a object of interest in the back, within the background, like hills behind it, or just or junk, you know, and be able to pick out a tiny little, say if it's a little drone. Bigger stuff is easier, but they're getting smaller and smaller. And so they're working on AI to see if that can help be able to help find those little spots, those little threats that might be sticking in there in that background. And they're making some good progress. That's one area.
Follow-up question. Where are we, U.S. versus other countries? Are we more advanced or less?
I don't have a good feel for that. It's hard to say. Because AI isn't in my area, I don't read all the papers. I don't know if anybody here has been reading papers on it. That's usually how you tell, is what papers are coming out of different countries and what they're doing. And I haven't been keeping up with that, to tell you the honest truth. I was pretty impressed with the thing today. I was like, man, I feel old. It's like, it's like all this advancements being made. I mean, it's great. It's great. I just, yeah. Anybody else?
So, wondering, you mentioned that the telescopes that you have on ground now would do a much better, as much of a better job as the Hubble telescope does with regard to imaging of the sky. So does that mean we don't need telescopes out in space anymore?
No, because of UV, you know, our atmosphere protects us from UV, and so we can't see in that. So you still get, Hubble can do well for that. But it showed how well adaptive optics worked, and it was really a game changer. But no, and then like James Webb, that's totally different. That's amazing. It's in such a different orbit. Kind of makes your head spin how they even get that to that orbit. Yeah.
And another follow-up question on the laser side. So you're talking about, lasers mounted on airplanes, so the turbulence is a big challenge. How about lasers on satellites?
Well, way back in, was that the 80s? The Reagan Star Wars. That's what they were looking at, was lasers on satellites. And it's funny you say that, because my first actual position at the lab was the tail end of the Star Wars era. And indeed, they were looking at adaptive optics and lasers on that, and gold-coated mirrors and things. And so I don't know anything recently. We're more looking, as the Air Force is airplane-based. And so that's probably a good question for the Space Force now, which we support as well. I have to say that the Air Force Research Lab, I always say that we're the research arm for the United States Air Force, but we're really the research arm now that we have the Space Force for the Department of the Air Force, which includes the Space Force and the Air Force. So it doesn't mean that they wouldn't take some of our research and apply that to space-based. Not sure what they're thinking at this point in time. Yes, sir.
Out of curiosity, does the AFRL collaborate or work with other labs in the state?
We work with a lot of different people all over the country.
How frequently?
We work with other folks in other labs of the Air Force Research Labs. Actually, the Air Force Research Lab is made up, I should put that up there, about 10 directorates. It kind of goes up and down and I lose track, but 10 directorates all across the country. And 2 of them are in Albuquerque. RD and RV, which is directed energy and space vehicles. But we have anywhere from the Aerospace Directorate, where rockets out in California in, why did I just blank out on the page? Yes, thank you. and then they do more of the aero effects stuff in Dayton, Ohio. Most of the directorates sit in Dayton, Ohio. That's the headquarters for AFRL. So they have sensors where they work on a lot of different, sensors. I won't go into more detail. But also materials. What else is in Ohio? Anyway, across there. So we work with them, but we also have collaborations with a lot of other folks and with a lot of universities as well. As if some of you may or may not know, talking to David about this, was that we have the Air Force Research Lab, both RV and RD up at Kirtland, have an educational partnership agreement with the main universities, the three main big ones in New Mexico, including New Mexico State, and it allows us to work with you folks without doing paperwork for each little project. And they renew them every 5 years. I'm not sure which office it has gone through on this, but we have folks that really like, we have really good mentors. I like to brag about my folks, and they're really good mentors, and the students that they find to work on different projects. And mentoring they do. UNM is closer, but we trying to expand better. It's always a hit and miss. But did I answer your question? I don't know if I answered your question. We actually work with some international folks as well. We have an agreement with Australia, and we had one that just finished up with South Korea. So, and we work the Navy a lot, the Army a lot. We actually like to joke that we're the Navy and the Army's favorite lab. They tend to come to us for, we do a lot of that basic research that goes out to all of DoD.
So you had discussed with us like what your journey was like going from NMSU to AFRL. So in the modern day where a lot of applications are just online, everyone applies at one time, what would you recommend to students to make sure that they kind of stand out from everyone else who's applying and kind of get to a place like AFRL?
Keep contacting us. Bug us. If we meet you at a career fair and give you information and we take your resume and you don't hear from us, we try to have cards or our QR code in the back. I finally put them on the back of all my business cards. And also, what would be really good, so how many students do we have in here today? Oh, wow, okay, great. So I'm going to advertise. We have a summer scholar program. It's too late to apply for this year, but it always opens up somewhere early October. And it's a great opportunity to come. It's a great opportunity for you to try us out and we to try you out. And if you just Google AFRL Scholars, it'll pop up. And you'll see a bunch of little ads or like job descriptions. And it should have the mentor's name. And you'll be able to put down your top 3. And I always advise students to contact the mentor because that shows them that you reached out. And if you have a conversation with them, they're pretty good about responding right away. And it doesn't guarantee a position, but it really ups the chances. And it's a really good program. We also have some other programs. If you go to AF Research Lab, I should have put all that stuff on the bottom. I didn't even think about that. I'll change that. AF Research Lab, all smooshed together, .com. And in there is, it goes to the main page of the labs, and you can look up all the different labs, all of the different directorates around the country. By the way, the Scholars Program is pretty much AFRL-wide, so you may find some if you want to go to Eglin, Florida, or Dayton, or whatever. And so there's opportunities all over. And I encourage those that, they might want to try one place one summer, maybe go another place the next summer. And once you kind of get in and you get to know a mentor, a lot of times they'll bring you back if it's a good fit. It's a really great way to find out if you're a good fit for us, and us to see if you're a good fit. See if it's a matchmaker there. So, yeah.
And you also get a security clearance, which is very good to put on your resume.
Yes, you do. You get a security clearance by being a summer scholar. Now, we've had folks that have come in just to get the security clearance, so don't do that. I hope that you come to work with us, too, and gain some experience and not just get the security clearance. Oh, I lost track.
Sort of along those lines, not necessarily engineer related, but with the experience and knowledge that you know now, what would you tell your undergrad self?
Oh, that's a good one. I would tell my undergrad self, don't be so doggone shy. And one thing that I realized was Dr. Giles had offered me a TA position. And I kept thinking, I'm in such debt, I have to go to school. And I wished I had taken that, and I would have gotten my master's and been better off right off the bat, and still probably made it to U of A. So that's one thing I would tell my undergraduate self. I do advise all, I think your professors would agree with me, looking at the way industry is today, I always say that a master's in engineering is probably one of the most profitable degrees. You get a PhD if you really want to teach, which is why I got mine, which I haven't taught yet, but I just might. I probably will. Or just you want to do research in a really dedicated area. It's a personal choice. It really is. But I really encourage you. It's only like a year and a half more. Why not just invest that time? It also, when I read resumes and I see, and you do a thesis and I see what your work is in, it just elevates you a little bit more in that area rather than an undergrad degree. Nothing against undergrad degrees, but it just gives you that little extra nudge.
Have you considered teaching a geometric optics course at the University of Southern New Mexico?
We've been talking about that. and the state of things going on now, who knows? Yes, I've even talked to my colleague. He says you should do that to get all my notes back out and put a course together. Be remote to begin with, but my sister probably wouldn't be unhappy if I moved closer. Anything else?
Going back to the opportunities for students, do you guys take SMART scholars?
Oh yes, we do. Now the best way we do SMARTs is our mentors will find summer scholars, and they say, you're perfect. Go apply for the SMART, and then we pluck them. Every once in a while, we have someone, and we also do cold hires from SMART. But predominantly, that's why I harp on the Summer Scholars Program, because it's really profitable in a sense to get you to know us. And if it's a really good fit, we track you through that, pipeline you through that. Yep, absolutely, yeah. So there's all kinds of programs. There's one called Premier College Internship Program. I don't know what level you guys are all in here, but it's between your junior and senior year of college. You work for the summer, kind of like a summer scholar, but you're on a different program called PSIP, Premier College Internship Program. Air Force loves acronyms. The government loves acronyms. I think the university likes acronyms too, don't they? And but what's nice about that is it follows on into what we call a Palace Acquire program, which is a long program that the Air Force has had, or DOD has had for many, many years. And it's, I call it like a three-year internship program, but really you're already a government employee. The first year you come on like a junior engineer, not like, you are a junior engineer. Second year we send you back to college, send you back for your master's, free of charge. We pay for that. And then the third year, you come back. You've got a master's under your belt, a previous year of experience. And then after the third year, you come on on a what I call a solid billet. It's not full. I say full time, but really you're already starting from that first year to earn a pension. Yes, we still have a pension program and a 401k and all of that. You start off as a civilian, a civil servant. And then we just convert you to a different type of personnel system when you're done with the program. You owe the government back 3 years for that, but the first year is that third year that you do, so only 2 more years. But we hope that you like us so much that you'll stay and that you won't leave. But and SMART is 1 for 1. So if you do 3 years of a SMART program, you pay back 3 or 5. The 5 is the limit. And stuff. So that's for undergrad, grad, and graduate. SMART is. I think I covered all of the. I should make a whole chart on that. Sorry about that. Good.
Can I ask you to follow up on, you said that your group has won awards for mentorship.
Mm-hmm.
And so can you maybe talk a little bit more about details in terms of what are some of the factors that are considered in those awards? And because I know you've talked to me about there at UNM that you meet with students there like at the Frontier Restaurant on Central, right? But so what else, what would you say are the main characteristics of that mentorship program?
Oh, the UNM one,
or just the overall within your group?
So in my group, we just have a lot of folks that are really dedicated to the next generation. I always say that it's our duty as scientists and engineers in our profession that we need to give back to the next generation because they got to come back to us. And so I harp on that a lot, and we have a lot of folks that have that. I hire them to have that mentality, you know, or I infect them with it, and they catch on. Also, some of our former summer scholars that have come in and now are a SMART student now full-time because they saw how they were mentored. They are now giving back to the next generation. So trying to make it a culture, more of a culture of mentoring, and we have such really good ones. They just they come up with excellent projects for their students, for the summer scholars. They really pay attention and teach them. It's not like, here, do this for the summer. Really work with them. We have one that he's probably been the best one. He's cracks me up. He's an aerospace engineer, and but we tell him he bribes them because they come in with AFRL shirts and all the other summer scholars are jealous. Like, how did you get that? Oh, well, our mentor gave us that, you know. But that I'm joking that a little bit. But he does treat them very well. But he teaches them. They're teachers, you know. They really are teachers, and as all you are, along with in mentoring and guiding them. And the program with UNM, they had gotten I can't remember, a title something or other grant years ago. Actually, it's been 10 years. It was 2015. And part of their grant had to be that they had to come up with a unique mentoring program. So we already had an EPA with them, Educational Partnership Agreement with them. So they came to us and we put together ideas, put together a STEM mentoring program. And so my division was the main one that really worked on that part of it, and then the space vehicles also we worked as a team. But they only could fund it for so long because of the grant, but because it was the most what's the word I'm looking for? Sorry, age. Most profitable one, most successful. That's the word I'm looking for. My God, most successful part of that whole program. That they were actually able to get funding to keep it. And to begin with, it was only with the AFRL, but then they were able to bring in Sandia and even industry partners to come in and mentor students. And it's really trying to get them over the hump of, you know, if they're coming in with not really knowing the math skills and they're having to take math to catch up, and then they're trying to get into the engineering programs or physics or whatever, and trying to keep them encouraged. Don't give up. Providing resources. We don't do tutoring, but we provide them through the mentoring program to get them the resources if they need tutoring help. It's also another person that's watching over them that can talk to the mentoring program to help them get these resources. And it's really those freshmen, sophomores, you know, the early ones, to make sure they don't leave. the program and it's become extremely successful. Really, really proud of it, you know. And I can put you in touch with the person that runs it at UNM. We don't really have, now that it's run by UNM, we don't have as much, we just provide mentors. And whereas before we were knee deep in how to get it all working together. We also did a lot of tours for the students to bring them and show them what we do. Because it's fun to see cool labs, right? And so that's another thing that we do. And for the one that asked about military, one of the main persons that was so adamant about keeping it was one of our captains. And he went and fought for that. He even went to IEEE, his IEEE group, to see if they could help fund it. And I think the university saw, or at least the engineering department saw, how passionate people were about it and how it was being so successful that, and I attribute a lot of that to our captain, and who now teaches at Air Force Institute Technology and stuff. So I hope, does that help answer?
Yeah, thank you.
And yeah, so I think mentoring is part of a culture